Hello everyone, now we will have a tutorial session and we will solve some numerical problems based on the discussion in our 4 previous classes. Problem number 1, the statement is a complete mixture activated sludge process is used to treat a wastewater flow of 2 mld having BOD 5 of 220 mg per liter. The biomass concentration in the aeration tank is 2300 mg per liter and the concentration of net biomass leaving the system per day is 50 mg per liter. The aeration tank has a volume of 200 meter cube. So, what is the hydraulic retention time of wastewater in the aeration tank and what is the mean cell residence time? So, these two we have to calculate from the statement on the basis of the statement. So, here we have Q, that is volumetric flow rate, that is equal to 2 mld and BOD 5 is equal to 220 mg per liter and MLSS 2300 mg per liter and XW is equal to 50 mg per liter, okay, and V is equal to 200 meter cube, that is the aeration tank volume. So, these parameters are given in the statement. So, this is a problem of secondary treatment using activated sludge process. So, we will be using the formula we have discussed in the previous class, like say for example, the HRT hydraulic retention time, we have seen that that is nothing but V by Q, where V is the reactor volume, the volume of the aeration tank and divided by volumetric flow rate. So, in this case volume is equal to 200 meter cube and Q is equal to 2 mld. So, 2 into 10 to the power 6 liter per day. So, this we can write like this. So, 200 meter cube divided by 2 into 10 to the power 6, that liter we have to again convert it into the meter cube. So, 1000 we are dividing this by. So, we are getting that is meter cube and meter cube by day. So, that will be coming into days unit. So, 0.1 days we are getting, and mean cell residence time, that is theta c, that we also know that total biomass present in the system, that is in the aeration tank, and net biomass leaving the system per day. So, we have seen that there are two stream. So, this is and then aeration tank, then it will come to your settling chamber and from settling chamber we will be getting one effluent and another will be sludge. So, some part will be recycled and some sludge will go out. So, there are two stream, outlet stream, that is your effluent water and this is your sludge. So, here total biomass present in the system is equal to volume of the aeration tank into MLSS concentration in the aeration tank. So, 200 meter cube into 2300 mg per liter, which is given there. So, this one. So, this equal to, we will convert it in unit, that is meter cube and liter. So, that conversion, so 10 to the power 3 liter we are getting this mg per liter and again we will convert it into mg to kg. So, multiply this term with 10 to the minus 6. So, then we are getting kg and ultimately we are getting the 460 kg, that is total biomass present in it, though this is the numerator part. So, denominator we have to calculate. So, net biomass leaving the system per day, that is equal to 2 mld into 50 mg per liter, that is 2 into 10 to the power 6 per liter per day into 50 mg per liter, that is equal to 100 into 10 to the minus 5 mg per day. So, that is 1000 kg per day, and theta c is equal to 460 kg by 100 kg per day. So, that is equal to 4.6 days. Then problem number 2, statement a completely mixed activated sludge process is to be used to treat wastewater flow of 510 meter cube per hour having soluble BOD 5 of 240 mg per liter. The concentration of soluble BOD 5 escaping treatment is 11 mg per liter. Design criteria are as follows: y equal to 0.4, k equal to 4 per day, kd equal to 0.07 per day, k is equal to 90 mg per liter, 90 mg per liter, and the concentration of MLVSS is equal to 2000 mg per liter. So, these are given. So, we have to compute the following: the treatment efficiency, the mean cell residence time, the hydraulic retention time, the volume of the aeration tank, and feed by microbial mass ratio, feed by biomass ratio. So, again the treatment efficiency, we can get this formula, efficiency equal to SO minus AC by SO. So, initial substrate concentration minus final substrate concentration divided by initial substrate concentration. So, we have initial BOD is 240 and final is 11. So, 240 minus 11 divided by 240. So, that is equal to 0.9542 or 95.42 percentage. So, this is the treatment efficiency. Next was the residence time. We need to calculate the residence time, that is theta c, and we know that we have this expression 1 by theta c equal to y k A c by k s plus A c minus k d. So, this is the expression. So, with the help of all these biokinetic parameter, we can get the value of theta c, and now we will put this. So, y equal to 0.4, it is given in the statement, k is equal to 4, it is given in the statement, and then S E, that is 11, and K S is given 90 plus S E 11, and then K D is equal to 0.07. So, then we are getting this equal to 0.104 per day. So, 1 by theta c equal to this one. So, theta c equal to 1 by 0.104. So, that is equal to 9.61 days. Then hydraulic retention time theta. So, that is equal to these expressions we have. So, theta c into y into SO minus AC by x into 1 plus theta c into k d. So, we will be putting those values here. So, theta c 9.61 we are getting, y we have 0.4 and SO 240 minus AC 11 divided by x, that is 2000, it is given. So, 1 plus theta c again 9.61 into k d equal to 0.07. So, by this expressions and solving it, we are getting 0.263 day. So, this is hydraulic retention time. Now, the volume of the aeration tank, that is V equal to Q into theta. So, theta is equal to 0.263 day. So, that is equal to 6.31 hours. We will have to multiply it with this. So, we will get this one. So, then 510 is the flow rate and this is the retention time. So, total volume is equal to 3218.1 meter cube. So, this is the aeration tank volume, and last one we need to calculate, that is F by m. So, F by m expression is Q into SO divided by V into x, and V by Q equal to theta. So, SO by theta into x. So, SO is 240 and then theta is equal to 0.263 in day, and then next equal to this one 2000, and then we are getting 0.46 mg per day. So, this is our F by m. Okay. So, next problem number 3, statement is air supplied to the activated sludge plant of the previous example at a temperature of 25 degree centigrade. The oxygen transfer efficiency is 10%. Assume the BOD5 is 67.5% of the ultimate BOD5. Calculate the volume of air supplied to the plant. So, this is a problem of aeration, basically activated sludge process. So, how much air is required, that we have to calculate, and in this case we have that formula, this one m O2 dot equal to Q into SO minus AC by F into 10 to the minus 3, that is unit conversion gram by kg, minus 1.42 into Px, where m O2 is mass of oxygen required per day, kg per day, and Px is the mass of sludge wasted each day in terms of VSS in kg per day, and F is the conversion factor for converting BOD5 to ultimate BOD, which is given in the statement, that is equal to 67% of the ultimate BOD5. Okay. So, that we will be using now, and this Px can be calculated by using this formula, as we have discussed in our previous class, that is Px equal to y observed into Q into SO minus AC by 10 to the minus 3. So, then we will be y observed, we will be calculating by using this formula, that is y by 1 plus theta c into k d. So, let us see the value of y observed first. So, y observed equal to your y value 0.4 in the previous statement. So, 0.4 here. So, 1 plus theta c we have calculated 9.61 and then 0.07 kd. So, then we are getting y observed equal to 0.239 kg ml SS by kg BOD5 removed. So, this is our y observed, and then we will put this value in this Px calculation. So, if we use this value in the Px calculation, so y observed equal to 0.239 here, and then we are having q, that is 510 meter cube per hour into 24 per day. So, we are meter cube per day, and then 240 SO and 11, that is equal to AC. So, that was mg per liter converted to gram per meter cube, same unit, same values will be there, and then here 10 to the minus 3. So, ultimately we are getting Px is equal to 669.91 kg per day. So, in this original expression, now we have to calculate this term, first term, and let us say the first term is equal to this one. So, 2510 into 24 into 240 minus 11 and then 0.675 into 10 to the power 3. So, that is the F value, the 67.5%. So, 0.675 minus 1.42 into this 669.91, the Px value we have calculated. So, that is becoming as 3201.26 kg per day of oxygen. So, the oxygen requirement we are able to calculate by using this formula is in the unit of kg per day of oxygen, but we are asked to calculate the air volume requirement. So, we have to think what is the volume or what is the mass of the corresponding air where this much of oxygen is available. Then we will convert it into the volume, and if there is some mass transfer efficiency is also given. So, that is 10%. So, that way we have to, there will be volume of air required 10% of oxygen transfer efficiency. So, then that also has to be considered here. So, this is our kg per day of oxygen. So, we are converting it to corresponding mass of air by dividing it with this 0.232, because mass fraction of oxygen in air is equal to 0.232. Then we are dividing it by 1.185, that is the density of air. So, we are getting this term, the volume of the air required, but since the 10% oxygen transfer efficiency. So, more volume of air will be required. So, we have to divide it by 0.10. So, then we are getting this amount of air is required, that is 1,16,443.33 meter cube per day. So, this is the volume of air required for this process. Now, problem number 4, determine the depth of a low rate trickling filter that has a diameter of 3 meter. The hydraulic loading is 0.17 meter cube per second, and the influent and effluent BOD5 are 260 mg per liter and 50 mg per liter respectively. The unit operates at 27 degree centigrade. Assume the empirical constants m equal to n equal to 1 and k 25 is equal to 0.1 meter per day. The packing media are rocks which have a porosity of 0.4 and a sphericity of 0.6. The geometric mean size of the rocks is 70 millimeter. So, similar type of problems we have discussed in our previous class also. So, this is a problem related to trickling filters, and you know that there is hardly any first principle based models for the predictions of the performance of trickling filters, and we have discussed one empirical model as mentioned here, that is AC by SI, that is equal to exponential minus KL AS into A by Q. So, actually it is where m and this is where n. So, m and n equal to 1. So, this has been written simply, and AS is the specific surface area which can be written as this 6 into 1 minus eta divided by psi into this one your diameter. So, this formula we have seen in our previous class. So, by putting this your porosity 0.4 and sphericity is 0.6 and 70 millimeter, diameter. So, we will have to convert it into meter. So, multiply it with 10 to the minus 3. So, we are getting 85.71 per meter. Okay, then this is your, that is meter square by meter cube basically. Now, again we have to calculate the value of k, because in our expression we have the value of k. So, that k value is given at 25 degree centigrade, but we need to calculate it at 27 degree centigrade. So, this is the relationship K 20 equal to K 25 into theta to the power 25 minus 27 minus 25. So, here K 25 is 0.1 and theta value is 1.08 and 27 minus 25 equal to 2. So, this one equal to 0.1166 meter per day. Then another term we have to determine the value of A, that is cross sectional area of the filter. So, that we are getting pi r square by 4. So, r pi r square or pi d square by 4, d is equal to 35 meter. So, pi by 4 into 35 square. So, then we are getting 962.113 meter square, and q is given that 0.17 meter cube per second, that is equal to 14,688 meter cube per day. So, this is the unit conversion. Now, we have all those values, then we will be putting the values now and using this formula to get the value of L. So, what we are getting? AC 50, SO 260, and then exponential, that is your the k, into we have to put the value of AS to the power n, that is 1, and L to the power m, that is 1, then L, and A by q to the power n, that is again 1. So, this is the expression we are getting now. So, from this unknown value is L or all are known. So, solving the above equation, the L value is becoming as 2.52 meter. So, now we are able to find out the depth of the trickling filter. Next, problem number 5, the statement is determine the size of a high rate trickling filter in which the sewage flow rate is 4 mld with recirculation ratio 1.5. The BOD of raw sewage is 260 mg per liter, from which 30% BOD is removed in primary settling tank, and the desired BOD of the final effluent is 35 mg per liter. So, depth is equal to 1.2 meter, it is given. So, we have to determine the size of this high rate trickling filter. So, this is again a problem related to trickling filter, and in the previous problem we have used one empirical relationship. Here we are going to use another empirical relationship, because the information which are provided, those are not sufficient to use the previous empirical relationship. So, we will be using this empirical relationship here, that is E is equal to 100 divided by 1 plus 0.44 into W by V into F, where E is the efficiency, F is the recirculation factor, and V is the volume of the trickling filter, and W is the organic load or BOD load in kg per day. So, these are the different terms used in this empirical relationship. Okay. So, here we will use this formula to calculate the volume, then from that we will calculate the area, because depth is given. Now, there are some other conditions. What is that? Say at the primary sedimentation tank we are having 30% reductions in the BOD, and initially is 260 mg per liter. This is our trickling filter, and it is coming to secondary sedimentation tank or other treatment unit. So, BOD 5 is reduced 30% before is entering to the trickling filter. So, YI what will be here, that is equal to 70% remaining. So, 260 into 0.7, so 182 mg per liter, and after treatment it is mandatory that 35 mg per liter is allowed. So, it is going to 35 mg per liter here. So, y is equal to 35 mg per liter. So, in this trickling filter we are inlet is 182, outlet is 35. Okay. So, this way the reductions in concentration, that is 182 minus 135, 182 minus 35 and initial concentration 182. So, this ratio multiplied by 100, that is 80.76. So, that is the efficiency of this process. Okay. So, this one calculation for the determination of efficiency. So, BOD influent minus BOD effluent divided by BOD of the influent into 100. So, that has been used to calculate the efficiency. So, this efficiency value we will use in our empirical relationship to find out the value of the volume. Now, what is the BOD load on filter in kg per day? So, 180, this is your concentration, and 4 mLD volumetric flow rate. So, this is the value we will get, 180 into 10 to the minus 6 kg per liter into 4 into 10 to the power 6 liter per day. So, that is 728 kg per day, this is BOD load, and recirculation factor F is defined as 1 plus R by 1 plus 0.1 R to the power square. So, this is equal to, in this case, 1 plus 1.5, it is given in this statement that with recirculation ratio 1.5. So, then 1.5 we will put it here. So, 1 plus 1.5 divided by 0.1 into 1.5 square. So, 1.89. So, recirculation factor is becoming 1.89, and then we will put these values in our efficiency expression. E is equal to 100 divided by 1 plus 0.44 into 728 divided by V into 1.89. So, this is your F and this is our BOD load. So, that is why W. So, then if we put this E value, we are getting, that is 80.76. So, that value we will put it here, and by solving E V is coming as 1314.06 meter cube. So, the volume is coming as 1314.06 meter cube. So, area will be how much? So, area will be volume by depth. So, 1314.06 divided by 1.2, the depth is given. So, this is our meter square, 1095.05 meter square. So, if it is the meter square area, so that area is equal to again pi d square by 4. So, we will be putting this expressions here, that is we will be putting this value here in this expression. So, 1095 equal to pi by 4 into d square. So, from that d value is coming equal to 37.349 meter. So, the depth is given, diameter is calculated. So, the dimension of the trickling filter we are able to find out. Next, problem number 6. Wastewater flow from a small community averages 3400 meter cube per day during the winter and 6600 meter cube per day during the summer. The average temperature of the coldest month is 10 degree centigrade and the average temperature of the warmest month is 30 degree centigrade. The average VOD5 is 200 mg per liter with 70% being soluble. The reaction coefficient K is 0.25 per day at 20 degree centigrade and the value of temperature coefficient is 1.09. Prepare a preliminary design for a facultative pond treatment system for the community to remove 90% of the soluble BOD. We have to make some preliminary design and we have to calculate, find the volume of the facultative lagoon to remove 90% of the soluble BOD and find the dimensions of 3 square lagoons in series with depth 1.5 meter. So, two parts, the first part we have to calculate the volume of the facultative lagoon and then second part we have to calculate the dimension of the 3 square lagoons in series with depth 1.5 meter. So, in place of one big lagoon, if we use 3 equal volume lagoon, with the same capacity, then what will be the dimensions of these lagoons that we have to calculate. So, there are two part of this problem. So, now how we can solve it? We have some design expressions we have discussed in our previous class. For lagoon system, we have S by SO is equal to 1 by 1 plus k V by Q, that is equal to 1 by 1 plus k theta, where S by S is the fraction of the soluble BOD remaining and k is the reaction rate coefficient and theta is the hydraulic retention time and V area, V reactor volume and Q flow rate. The units are given here, and we also have one formula for the k value correction. So, this k t is equal to k 20 into theta to the power t minus 20. So, in this case the theta value is given, that is 1.09, theta is equal to 1.09, it is given, and t value we have different cases, winter and summer. So, one minimum temperature, another maximum temperature. So, one is 30 and another is your 10. So, then we will be calculating these k t values for summer and winter, that is k 30 will be getting 0.25, that is for k 20, and then 1.09 to the power 30 minus 20. So, we are getting 0.592 per day, and for winter k 10, that is equal to 0.25 into 1.09 into to the power 10 minus 20. So, that is equal to 0.106 per day. So, now two different situation and two k value we have got, then we have to get the value of volume requirement. So, this V value we have to calculate. So, here the expression is S by S equal to 1 by 1 plus k into V by Q, that is equal to S is equal to 20 and S O is equal to 200. So, this we can, this S we can say also S E, equilibrium of the effluent substrate concentration or BOD concentration. So, 20 by 200 we are getting this side, and right hand side 1 plus k for summer, that is k 25. So, 0.592 into V by Q, Q is same for both the cases. Now, Q is also different, Q is also different into different situation. So, in this case it is 6600 Q. So, by putting this value 6600 and solving this expression, we are getting the value of V as this one 100,337.84 meter cube. So, this is for this is the volume for summer, and for winter the left hand side is same 20 by 200, but the right hand side value, that is Q value, is different and K 10 value is also different. So, 1 by 1 plus 0.106 into V by 3400. So, we are getting V value is equal to 288,679.24 meter cube. So, the first part of the problem is calculated, okay, and second part we have to see the volume of the lagoon when the three equal volume lagoons are used in a series. So, let us say, so this is our first, second and third lagoon, all are having the same volume V I, V I and V I. So, here we get the outlet from 1 is the inlet to 2, outlet from 2 is the inlet to lagoon 3, and then it is going out, and then it is going out. So, for a single unit, if we say that S by S O equal to 1 by 1 plus k V by theta, and then if it is n in series, so that expressions will be this one S n by S O. So, this is our S n after n numbers, S n by S O, the initial which we had, that is equal to 1 by 1 plus k into theta by n to the power n. So, this number of units we have, so we will be dividing it k theta by n. So, theta is the residence time. So, now we have 3 tanks, so equally distributed. So, that is theta by n, this is for any one unit. So, k into theta by n, and as number of series in series number of units are there n. So, that n will be multiplied to the whole of it. Okay. So, this is the formula we are going to use, because theta will be replaced by V I by Q, V I by Q we will be using here. So, at summer we will be having 200 by 20 is equal to 200 by 20, that is equal to this one, we are taking the inverse of it. So, 1 plus 0.592 into V I by 3 into 6600, this is the K value we have calculated for 25 degree centigrade. So, V is equal to 38611.16 meter cube, but for winter, so 200 by 20, that is equal to 1 plus then K 0.106 into V I divided by 3 into 3400 to the power cube. So, we are getting V is equal to 111087.11 meter cube. Okay. So, now second part is completed. Up to this in this class. Thank you very much for your patience.